Hello everyone and welcome back to Exam Ignite YouTube channel. So today we are starting with the digital communication subject of the 5th semester of core BEC503. We will be starting with the module 1, that is the first part is bandpass signals to equivalent low pass. In that now for this making this notes I have referred the textbook as well as the model question paper and 2 previous year question papers to note down the important things that we have to focus on the exam related topics. So first topic here is the bandpass signal to equivalent low pass. In this, the first important is Hilbert transform. As I said, this is a very important. You need to know the definition and the properties of Hilbert transform. And the next is the pre-envelope. This is also important because it is being asked in the last year as well as in the model question paper. Next, you need to know the complex envelope of the bandpass signals. Next, the canonical representation of the bandpass signals. And here it is being asked in both the forms, that is in the Cartesian and the polar representation. Coming to signaling over AWGN channels, here geometric representation of signals, then GSOP. This is an important for a problem. Conversion of continuous AWGN channel into a vector channel derivation. Then optimal receivers, that is in the coherent detection we are having 3 ML decoding, coherent relay receiver and matched filter receiver. These are very important, especially the last two. And next, these are some of the problems that have been asked in the papers as well as in the model question paper. So going ahead with the topic, firstly, bandpass signal to equivalent low pass. Do note that I'm using this short form, that is S bar L has signal and S bar B has a symbol in the future videos. So firstly, we'll start with the Hilbert transform. Before going to Hilbert transform, we need to have a some brief about the Fourier transform. It is evaluating the frequency of a content of a signal. Basically, Fourier transform is so mathematical basis analyzing the digital analyzing and designing the frequency selective filters. This is what Fourier transform is. Here, what separation of the signal on the basis of the frequency content. For what? Fourier transform. But coming to the Hilbert transform, separating the signal based on the phase selectivity. This is called as the Hilbert transform. Mathematically, what you can say it is the analyzing and designing the phase selective filters. Next, here FT means it is the Fourier transform, Fourier domain analysis. HT means it is time domain analysis. Coming to the main important, that is the definition of the Hilbert transform. What you have to write is in the phase, if the phase angle of all the components of a given signal are shifted by plus or minus 90 degree. This is about phase. Then the resulting function of the time is called as the Hilbert transform of the signal. So Hilbert transform of x of t, it is given as it is denoted by x cap of t, and then that is 1 by pi integration of minus infinity to infinity x of tau divided by t minus tau into d2. Consider this as equation 1. Then taking the inverse transform of the Hilbert transform, we get x of t as minus 1 by pi integration of minus infinity to infinity x cap of tau divided by t minus tau into d2. So these are the two main definitions you need to write. Next, from the definition of x cap of t, it is the convolution of x of t with a time function, that is 1 by pi t. So you can write it as x cap of t has x of t into the 1 by pi t. So consider this as equation 3. Next is, we know that the convolution in time domain is a product in frequency domain. That what you can write it as Fourier transform of x of t can be written as x of x. So similarly, for Fourier transform of 1 by pi t, it is written as minus j signum function of f. This signum function can be given as 1 by 1 if it is f is function is greater than 0, and it is 0 if it is equal to 0, and it is minus 1 if it is less than 0. So from the equation 3, what you can write it as, you can substitute this, take the Fourier transform of whole equation, then you will get it as x cap of f is equal to x of f of minus j signum function of f. So on taking the x of f to the right side, we get this equation 4. So how is this written as? You can write it as when x of t is taken Fourier transform, we get x of f. To that, we give an input of minus j signum function. So that gives us x cap of f, and then taking the inverse Fourier transform, we get it as x cap of t. It is a two-port device where we produce the phase shift. So minus 90 for all the positive frequency of input, and it is plus 90 for all the negative frequency of input. Next, coming in representing them, this is the amplitude representation, and this is the phase representation. So application of this is Hilbert transformers. It is generation of the single sideband, and representation of BPS, the mathematical bandpass signal mathematical. Next is Hilbert transform pairs. So here we are having two pairs. One is time function and the Hilbert transform, where m of t cos 2 pi fct is given in Hilbert transform has m of t sine 2 pi fct. For the sine 2 pi fct, it is minus cos 2 pi fct. Cos 2 pi fct, sine 2 pi fct. Sine 2 pi fct, it is minus cos 2 pi fct. Sine t by t, it is 1 minus cos t by t. And dou t, delta t, that is 1 by pi t. 1 plus 1 divided by 1 plus t square is 1 divided by 1 plus t square only. 1 by t is minus pi delta t. Now coming to the problems on Hilbert transform, firstly, x of t, it is given as cos 2 pi fct. You need to take the Hilbert transform. So what basically this is a phase shift. So what we are going to do is we are going to minus pi by 2 to the angle. So cos of 2 pi fct minus pi by 2. Now what, take the minus common out. So what, pi by 2 minus 2 pi fct. Finally, you know, cos minus theta is cos theta. So write it directly, and next it is cos pi by 2 minus theta is sine theta. So our answer is x cap of t is sine 2 pi fct. Similarly, in this equation, we are having one cos and having one sine. So do it separately with the formulas and taking the minus out, and so you will get the answer like this. So if we consider the e minus j 2 pi ft, then what happens is you have to write it as e minus j theta is written as cos theta minus j sin theta formula. After that, you need to minus pi by 2 on for both the angles. Then take the minus out, and then you will get the 2 cos theta plus j sin theta, and for that you need to make it as sin theta plus j cos theta. Also, you can simplify this further as taking the j as common out, and then multiplying the j inside, then you get j square. So j square is minus 1, so that becomes plus. This is in the form of j e power minus j theta, so that can also be written here. Now coming to the properties of Hilbert transform. So firstly, x of t, let us assume to be a real valued function. So our first property is defined as a signal x of t, and its Hilbert transform is what, x of t have the same magnitude spectrum. So that is x of f magnitude is equal to x cap of f. So we know that x of f is equal to a signum function of minus j sine a signum function of f into x of f. So taking the magnitude on both the sides, we know minus j signum function of f is 1. So finally we get this, it is proved. This is our first property. Coming to the second property, it is if the x cap of t is the Hilbert transform of x of t, then you can say the Hilbert transform of x cap of t is minus x of t, taking the Hilbert transform of the Hilbert transform. So here x of t is what? First it is taken an Hilbert transform, then we get x cap of t. Again, if you take the Hilbert transform, you get minus x of t. That is minus j signum function of f minus j signum function of f. It becomes j square signum square function. So minus 1 into 1, it is minus 1 for all the values of f function. So hence it is proved. Then coming to the third property states that a signal x of t and its Hilbert transform x cap of t are orthogonal over an entire time interval of what? Minus infinity to infinity. So if you take an integration of minus infinity to infinity x cap of t into x of t, then you can solve it like this. First, you have to write them in the form of frequency domain, but you know that x cap of f is what? Minus the signum function of x of f. So then what is minus f? It is minus the signum function of minus f into minus f. So you get this expression. So on applying and solving this, we get this has our odd function and this has our even function. So integration of odd function over minus infinity to infinity, it is what? 0. So 0 into anything is 0. So hence it is proved they are orthogonal. One is x of t and the Hilbert transform, both of them. So next is our property 4. Property 4 states that if C of t and M of t are the signals with non-overlapping spectra, where M of t is what? It is having a low frequency signal and C of t is having a high frequency signal, then you can write it as M of t into C of t is equal to M of t into Hilbert transform of the C of t. So this is our fourth property. So let's move on to the next, that is pre-envelopes. Here, firstly, you have to derive the pre-envelope. For that, first we will consider the x plus of t has x of t plus j x cap of t. So what x plus of t is? It's a pre-envelope for the positive frequency. Here, this is our real and this is our imaginary part. So let's consider the Fourier transform of the equation 1. We get x plus of f is equal to x of f plus j of minus j signum function of f into x of f. So here minus j into j, we get the j square, which is 1. So x of f plus signum function of f into x of f. Taking the x of s as common, we get 1 plus signum function of f. So what a signum function is defined as I said it before. So for this, you go on applying for f greater than 0, it is 1. So I'll put 1 here. If you put 1 here, it becomes 1 plus 1, that is 2 x of f. If you put 0 here, it is x of f. If you put minus 1 here, this gets cancelled, so you get 0. So based on that, you can write like this for the positive frequency. So if for the positive frequency, the pre-envelope has no frequency component for the negative frequency, and it can be represented like this. So the first is for the amplitude spectrum of the low pass signal. This is the representation, and this is the amplitude spectrum of the pre-envelope of the positive frequency. You can note here there is no frequency component in negative part. Now let's go to the pre-envelope of the negative frequency. So that is given by x minus t. That is as x of t minus j x cap of t. So taking the Fourier transform of this and similarly multiplying, taking x of s as common and substituting all, we get in the reverse order. That last time we got this first, second, and third. This is in the reverse order. So here you can say pre-envelope has no frequency component for the positive frequency. So you can write this as an amplitude spectrum of the pre-envelope for the negative frequency. There is nothing for positive part. Next, what the procedure to find pre-envelope is, first you have to determine the Fourier transform of x of f, that is x of f of the x of t. Then you need to write the x plus of f in terms of this to find the x plus of t, or you can do for x minus of f also. And next we have to evaluate the inverse Fourier transform of that to obtain this x of t. Finally, next is a complex envelope of bandpass signal. So consider an x of t of its Fourier transform x of f. It has a band frequency of 2 omega and centered about the frequency of plus or minus fc. So this is called as bandpass signal. So if it is fc has a carrier frequency and a very high compared to the bandwidth of 2 omega, then that is narrow band signal. So the pre-envelope of the narrow band signal x of t with its Fourier transform x of s, it's centered about the frequency plus or minus fc. That can be given as x of t is equal to x dash of t into e power minus j 2 pi ft. So this is given as equation 1, where our x dash of t is a complex envelope here. So representing that, this is our amplitude spectrum, and for the bandpass signal, this is how it looks like. In the pre-envelope, this is its position, that is fc minus omega, fc plus omega. For our complex envelope, that is x dash of s, it is 0, and from minus omega to plus omega. Next is the canonical representation of the bandpass signal. Here, x of t first we will consider as the real part of the x plus of t. So it is given as x of t is equal to real part of x dash of 2 pi fct. So next, x dash of t is what, as I said, is a complex value. So that includes two parts. One is xi of t and xq of t. So xi of t plus j xq of t. So xi of t, these two are the real value of the low pass function. So using this equation 2 in the canonical form, you need to find out this expression. This is the derivation. So how you do that? Here xi of t, it is an in-phase component, and the xq of t, it is a quadrature component. So starting with the how to do is, you have to substitute this equation 2 in this equation 1 in this part. So on substituting that, you get this second line. So you need to multiply this part to the xi of t plus jxq of t. So you get the real part and the imaginary part separately. On combining the real part, we get this equation 3. So final equation is obtained. So next, moving on to the graphical, that is you need to represent them in the graph. So first is it is the quadrature component. For the quadrature component, the angle is tan inverse of xq by xi, and then it is my square root of xi squared by xi square plus xq square. This is our quadrature component. And coming to the imaginary part, here it is a phasor representation of the complex exponential. It is the angle having the angle of 2 pi fct, and it is rotation having 2 pi fct with a magnitude of 1. So this is a real axis. So combining both of them, what happens here is you need to add up the angles you need to add, and the length should get multiplied. So what is the length here? Here the length is square root of x square I square plus x q square plus 1. So that gets multiplied, and these two angles are there, tan inverse and this 2 pi fct, they get added. So that is how it is represented like this. So this gets added. So you can see this is rotated at xi and xq, and rotation happens in 2 pi fct, and this is the projection of time varying phasor on the real axis. This is the multiplication of the complex envelope by complex exponential. Next, we will move on to the another one block diagram part, where xi of t and xq of t are the low pass signal with a band limit having of minus omega to plus omega. So these signals can be derived from the band pass signal x of t as shown in this figure. So in this figure, you can observe this is a derivation of xi of t, that is analyzer part. What happens here is x of t is given as an input to two adders. Here what happens, you need to give one oscillator with an input of cos 2 pi fct, and also here sin 2 pi fct along with a minus 90 degree phase shift. So when you give that, here we are having one low pass filter which gives an output of half xi of t, and here another one low pass filter which gives an output of xq of t. Coming to the figure E, this shows how to reconstruct the x of t from the xi of t. And as I said, we got two components, xi of t and xq of t. We need to give them as an input along with an oscillator with cos 2 pi fct and minus 90 degree phase shifter with sin 2 pi fct. So what do you get? That gets added up, and finally we get our x of t. So this is a reconstruction of x of t, and this is the synthesizer. Okay. Next is geometrical representation of signals. So consider M. M is what? It is an energy of the signals. Signals S. So signal representation is given as Si of t here, with Y varying from 1 to M. So these N energy signals can be represented using the N orthogonal basis function, where M is less than N. So any signal that can be represented in the linear combination of this on the basis of like this, you can represent any signal. So where Si of t1, Si of t, it is given as summation of j is equal to 1 to n, Sij, phi j of t, and j is equal to 1 to n. So how do you represent that? You represent it like this, Si1 and Si2 till Sin. What do you get? That gets added along with the phi 1 of t, phi 2 of t, and phi n of t. And finally that gets added and we get our Sit. So assume to be a noiseless channel. If it is noiseless channel, then Si of t is given as input along with the phi 1, phi 2, and phi n. Finally, that is integrated in an integrator. Finally, we get a separate Si1, Si2 like that Sin. So now you need to derive. So let us consider Sik, Si of t and phi k is equal to j is equal to 1 to n, Sij into phi j of t to phi k of t. This, let us consider this as A equation. So for noiseless, what has happened here? It is integrated from 0 to t. So assume k is equal to j and substitute that Si of t plus phi j of t is equal to summation of Sij. Okay, next we will move so that we need to know here Sij. So Sij is equal to what? It is Si of t into phi j of t into dt. That is, you need to integrate. where SI is SI1 to SIN. So any signal that can be represented in an n-dimensional vector, it forms a Euclidean space that is known as our signal space. So that is represented like this. So signal space, that is SP, SI, where our SP is nothing but SI transpose itself. So SI and its transpose, SI and its transpose. So finally, on multiplying this gives us the square component. So finally, we can write, therefore, has the signal space is equal to summation of j is equal to 1 to n into SI square. Sij square. Assuming the two vectors Si and Sj, so cos theta is equal to substitute that. So Si is, we know, Si transpose, and finally theta ij is cos comes right side, and this we get as our equation. Next comes GSOP, which is a Gram-Schmidt Orthogonalization procedure and an important topic in this module. It is the geometrical representation of the energy signals will be given by this GSOP procedure with the help of complete orthogonal set of the basis functions. So let us consider M as our energy signal set, that is S1 of t, S2 of t till Sm of t. The first basis function, that is for what? Si of t, right? That is the first basis function. So that is given as what? Phi 1 of t. Phi 1 of t is equal to what? Si of t divided by square root of E1. This equation is very important and we will consider this as equation 1, where our E1 is an energy of the signal, this S1 of t. Now, how do you write this S1 of t? Cross multiply this here, square root of E1 into phi 1 of t. And S1 of t is equal to what? S11 phi 1 of t. So where our coefficient S11 will be equal to square root of E1, and phi 1 of t is having a unit energy. So integration from 0 to t, this phi 1 square of t is equal to 1. Now using the signal S2 of 3 we'll consider. We define the coefficient for S2 of 1. So we define for S1 of t, now we define for S2 of t. For that, first we have to define S21. That is given by integration of 0 to t, S2 of t into the phi 1 of t. This is dependent on the phi 1 of t. Now we are having an intermediate function called as G2 of t. So G2 of t, it is given by S2 of t minus S21 into phi 1 of t. So here G2 of t, it is orthogonal to what? This phi 1 of t over the interval minus t to over the interval 0 to capital T. So this is the second basis function, hence therefore can be given as phi 2 of t as what? G2 of t divided by square root of G2 square of dt. So we know G2 of t, we substitute it here, and we know G2 of t, we will write it here. So finally, integration of 0 to t phi 2 of t, we will consider it as 1. So from the above, we can say this is also phi 1 of t and phi 2 of t into dt, that is 1. So from 0 to t, it is 0. So hence you can say these two are the orthogonal pair as required. So on continuing that, we need to define them generally. So to define them generally, we are having the third equation. To this equation, write it in the form of ij format. You get the general equation for the as equation 7. And similarly, the second equation, write it in the form of ij. You will get the 8th equation. And similarly, write the 4th equation in the terms of ij. You will be getting the 9th equation, which forms the orthogonal set.